as well as a force having the ability to change the motion of an object, i.e. to produce acceleration or deceleration, that sort of thing, a force can also cause an object to rotate. It can have what we call a turning effect. And the name given to the effect of a force, the turning effect, is the word moment. Just please take note that that is nothing to do with the word momentum, studied in the previous topic. Momentum, mass times velocity, a totally different concept. So please just make sure you do not confuse the word moment with momentum. All right, so how do we define the moment of a force? It's defined as force times perpendicular distance from the line of action of the force to the pivot. So let's have a look at a diagram to illustrate this. So we've got this green body up here. Let's say that this is a body at that point there where I've put the cross. That's going to be our pivot, the point about which the body is able to rotate, sometimes also called the fulcrum. Let's apply a force. Let's apply it here. Now at this stage, I'm going to make that force perpendicular to the body itself. And then we have got a perpendicular distance here. And so we define the moment of that force as being the force times the distance, FD. Now we don't have a symbol to represent the word moment, though we'll come across another word soon called torque, which can be represented by a symbol. The SI units, Newton meters, force times distance, and so we just leave it as Newton meters. Looking at a couple of little examples here then. In the left-hand example, similar to the previous page, we've got a force acting then perpendicular to the surface, and so the moment is force times distance. But in this right-hand example, the force is acting at some angle to the surface, and so if you used x, x is not the perpendicular distance from the line of action of the force. So what we need to do is we need to project this force backwards, the line of action of the force, until we hit the point where we've got that perpendicular. And so the distance that we would use in doing the calculation would be that perpendicular distance, F times D. So just watch out for that. In terms of your notes, I think just having written the diagram from the previous page, I think it is worth just writing down this right-hand diagram there. Let's have a look at a couple of simple examples then. 250 Newton force being applied to a wrench, a spanner, trying to tighten the nut on the wheel of a car, and we're asked to calculate the moment. So moment equals FD equals 250 times, and we've got to be a bit careful, distance has to be in meters, times 0.30. And so we get 75 Newton meters there. And the diagram on the right-hand side here just sort of shows a person using a spanner. In two cases, here the hand holding the spanner is a long way from the nut, which is effectively the pivot or the fulcrum. You're going to get a lot larger moment than if you tried putting the hand there. Apply the same size force, but much closer to the fulcrum, much less turning effect. Second example here, again tightening up the nut on a wheel, but we see that there's a bit of an angle. What we're told is that we've got 190 Newton force here. I think we can assume that that force is still acting in that direction there. But if we want the perpendicular distance, we need that horizontal distance there. So we've got a little triangle that we need to think about, a right angled triangle, like so. We've got an angle of 15 degrees. I think we're going to need to assume that the spanner is the same size as in the previous example, which was 30 centimeters. All right, so the hypotenuse is 30 centimeters. We're trying to find this side here, which is the adjacent side, so it's going to be cosine. So D is going to be 30 cos 15 degrees. Sorry, not very well written there. And so if we work out 30 cos 15, we get 28.97 recurring, so it's really 29.0 centimeters. So the moment, in this case, force times distance, force was 190 times 0.29, remembering to change to meters again, 55.1 Newton meters. All right, moving on from moments, just an extension of that idea to something called what we could know as a couple. Now we've got the definition of a couple here, and there's a few key things about that. You should be able to quote this definition. So it's two forces, there's the couple. They have to be of equal magnitude. They have to be acting in opposite directions. They have to be acting in such a way that their lines of action are parallel but separate. All right, so if we look at the diagrams shown here, all right, so we've got two forces that are equal in magnitude. They're acting in opposite directions. They are parallel to each other, but they are separate from each other. So in a case, again here, the lines of action here are separate. So again, we have a couple present. The situation where you would not have a couple would be if you had two equal and opposite forces acting parallel, but along the same line. In this situation here, there would be no turning effect, no torque applied. So let's do a look at the size of the moment produced by a force then. So let's get rid of that, I don't know where that came from. We've got F1 here acting this distance away, so F1 times D over 2, the moment produced by this force, F2, F2 times D over 2. So if we want to figure out the total moment, it's going to be F1 D over 2 plus F2 times D over 2. But remembering that F1 and F2 are the same, so it's going to be effectively F times D over 2 plus D over 2, which is D, F times D. So if we want the moment produced by a couple, it is simply a matter of calculating the, let's say, well, we call it the torque. I've got to use the word moment here. I'm going to switch across and use the term torque. And we can represent that by the Greek letter tor. And so the torque produced by a couple is F times D. Important little formula there. So that's simply, the magnitude of the force. It's the magnitude of either force. So you don't double it. And that's simply the separation between the two forces. So let's have a look at one example here. We've got a spinning top. You're applying a force of 5 newtons, 5 meters apart on the shaft of the top. So here's just a plan view here of this shaft here. And the diameter of that shaft is 5 millimeters, not the radius, the diameter. So we're applying a 5 Newton force here, a 5 Newton force here. That is a couple. It produces a torque. The torque is got by calculating the magnitude of one of the forces times the separation, 0.025 Newton meters. And the final point that I want you to take note of is that when you do apply a couple and get a torque acting on something, you get pure rotation. A body will spin without being shifted sideways.